Welcome, Atlos. Today, welcome you to the very interesting concept called derangements. It was back then in 1800s, a famous mathematician wanted to try out this concept. When things don't go to the exact places. Suppose there is one letter and there is only one envelope, corresponding envelope of it. So this letter one can go only to envelope one. So there cannot be a dearrangement in that. Derangements is basically de-arrangements, meaning wrong arrangements. But if suppose there are two letters and two corresponding envelopes, so there can be a if letter one goes to envelope one and letter two goes to envelope two, that is called as proper arrangement. But if letter two goes to envelope two and letter one goes to envelope two and letter two goes to envelope one, this is called as a proper derangement. And there is one derangement happening here. One derangement. Okay. So this concept expands, and the number of ways in which this can be seen is going to be more in number if there are going to be more letters and more corresponding envelopes. Okay. So in that way, if you just think about it, so all these letters, there are corresponding envelopes. So there are going to be n letters. Correspondingly, there is going to be n envelopes. So the number of ways in which this n letters will go into envelopes, not necessarily in the correct order, will be n factorial ways of distribute. In fact, it will be the total number of ways to distribute this letters to envelopes. Okay. So out of which, for instance, let's say if there is one envelope which is going correctly to the corresponding one letter going to the corresponding envelope. So which letter we don't know. So out of the n letters, if I choose one letter and let's say that is going to the corresponding envelope, now there will be n minus 1 letters. This n minus 1 letters will be again redistributed in n minus 1 factorial ways. So this is the case of saying one letter went to the right envelope, and we are just writing n minus 1 factorial for the, and others are distributed. When others are distributed, when I say, it could also mean that there are also some letters going to the right envelopes, which we do not know. So what we are trying to do is, we are trying to do inclusion exclusion principle. This was the total number of ways. From this, we are just trying to remove this way, where like one letter went into the right envelope. Now let's say there are two letters which went to right envelope. Two letters went to their right envelope, and others were distributed. So this would mean again, out of the n letters, which two letters went into the right envelope, and the remaining letters will be n minus 2 letters, and they are being arranged. So this will go like a plus minus plus minus. So you can just take the help of our A union B formula for understanding. In A union B formula, so you know the formula goes like n of A plus n of B minus n of A intersection B. So here there's like single sets, like they had a positive sign. When it came to intersection of two, it became a negative sign. So it goes like positive, negative, like that. Even in your formula of n of A union B union C, if you had known the formula, the single set all had positive sign, n of A plus n of B plus n of C. And the double sets, they all had negative signs, minus n of A intersection B, minus n of B intersection C, minus n of C intersection A. And three sets, they again came out to be the positive thing. So this is the idea behind inclusion exclusion principle. So that's what I've shown you here. So if you group up all this formula, you can understand n factorial can be actually brought out common, and 1 minus 1 by 1 factorial plus 1 by 2 factorial minus 1 by 3 factorial, so on till the 1 by n factorial. So this will be the formula for derangements. Okay. So this is a very interesting concept. If you just rewatch this video once or twice, you will actually understand how beautiful mathematics has created this. I'll just do one question for this, and we'll meet in another follow-up video for this derangement concept. So here the question is, there are seven letters. There are seven letters, okay, and seven envelopes. Seven letters and seven envelopes. So they are asking us the number of ways. They're asking a number of ways such that exactly three go into right envelope. So again, here you have to understand, we do not know which three goes into the right envelope. So out of seven letters, you need to choose those three. So that's seven three ways, seven C three ways of choosing which three goes into the right envelope. So the remaining there'll be four letters and they have to be deranged. So that's what they mean by saying only exactly three goes into the right envelope. So 7C3 into D4 should give us the answer for this question. So 7 NCAR formula 7 factorial by 3 factorial into 7 minus 3, which is 4 factorial. I have to expand D4. For D4, use this formula. So it will be 4 factorial times of 1 minus 1 by 1 factorial plus 1 by 2 factorial minus 1 by 3 factorial plus 1 by 4 factorial. So this 4 factorial gets cancelled off. So 7 factorial can be written as 7 into 6 into 5 into 4 into 3 factorial divided by 3 factorial. 3 factorial gets cancelled off. So here 1 minus 1 goes. So I have 1 by 2 minus 1 by 6 plus 1 by 24. So I have to reduce this down. So LCM will be 24. So I'll have 12 minus 4 plus 1 by 24. And here you have 7 into 6 into 5 into 4 into this. So 6 4s are 24. That will cancel out with this 24. So finally I have 35 into 12 minus 4 plus 1. That's 12 minus 4 is 8. 8 plus 1, 9. So 35 into 9. So 3, 1, 5 will be the right answer. That will be the total number of ways in which exactly three letters alone go into the right envelope and all the remaining getting deranged. Okay, hope you like this concept of derangements, people. We'll meet in the next video. Thank you.